Hi all, I am Fathima CS, Assistant Professor in the Department of Integrated Chemistry, MES College, Marampally.
As I said, we are going to learn the concept geometrical isomerism. Before, before that, we have to understand the concept of isomerism first. So, isomers are molecules that have the same molecular formula but different arrangements of atoms. So, as you can see in the image, these are the examples of isomers, that is normal butane and isobutanes. These two compounds have same molecular formula but they have different structural arrangements. So that is why they are called as isomers. So the isomers can be classified into two. So the next slide is about the classification of isomers. So broadly, we can classify the isomers into two: structural isomerisms and stereoisomers. So structural isomers defined as the molecules with same molecular formula but different arrangements of atoms. And as we come to the stereoisomers, stereoisomers have same molecular formula and same arrangements of atoms, but here the orientation of atoms in space is different. So stereoisomers can further classified into geometrical isomerism and optical isomerism. So this is all about the introduction, and we are going to specific, that is about geometrical isomerism. So we are going to learn about geometrical isomerism in alkanes. Geometrical isomerism is a type of stereoisomerism that occur when there are two or more possible arrangements of atoms in a molecule due to restricted rotation around a double bond. And it is mostly seen in alkenes. And in alkenes, the carbon atoms in the double bonds have different groups attached to them, resulting into two possible geometrical isomers, that is cis and trans. On conclusion, we can say geometrical isomerism in alkenes means cis and trans isomers. So we are going to learn about cis and trans isomerism now. Cis trans isomers in specific. Cis isomers have same group on same side of double bond, while trans isomers have same groups on opposite sides of the double bond. Let us see what is meant. As you can see here, the cis isomers have same group in the same side of double bond, and the trans isomers have same group in opposite sides of the double bond. Okay, that's what it means. So what is the key difference between the cis and trans isomers is about the arrangement of atoms in the space. That's why it's called geometrical isomerism. And this results in different physical and chemical properties as well, like melting point, boiling point, solubility, etc. So, as I said, this is an example of cis and trans isomers. Cis isomers contain same group on same side of the double bond, and trans isomers contains same group on opposite sides of the double bond. Let us see the significance of cis and trans isomers. Cis trans isomers is significant in organic chemistry because it can affect the reactivity and properties of molecules. For example, some cis trans isomers may be more reactive than others or may have different solubility or stability properties. Okay, so understanding cis trans isomers is very important in organic chemistry because it leads to difference in properties. Okay, so let's see the next slide. It's about the properties of geometrical isomerism. And here, three properties are enlisted. First one is boiling and melting point. The geometrical isomers, that is our cis and trans isomers, may have different boiling and melting points because of their differences in intermolecular forces. And the next property is solubility. The geometrical isomers, that's our cis and trans isomers, may differ in solubility as well because of their differences in polarity and hydrogen bonding. And coming to the reactivity, the geometrical isomers may also differ in the reactivity due to their difference in molecular structures and bond angles. Okay, that's all about the properties of geometrical isomerism. And coming to the applications of geometrical isomerism, we can find the applications in various fields, and specifically in these three fields: pharmaceutical industry, agricultural field, as well as food industry. So in pharmaceutical industry, the geometrical isomerism plays a crucial role in the development of new drugs. Okay, certain isomers can have different biological activities which can affect their efficacy and safety as well. So, while we discussing the cis and trans isomers of the same compound, cis may be pharmaceutically active and trans may be inactive. So, the cis variety can act as a drug and trans variety cannot. And coming to the agricultural field, geometrical isomerism is also important in the development of new pesticides and herbicides. Different isomers can have different effects on plant growth and insect behavior. As I said, in the pharmaceutical industry applications, the cis variety may be active and trans variety may not. So that is the application of geometrical isomerism in agricultural field. And coming to the food industry, geometrical isomerism is important in food industry as well for the production of certain flavors and fragrances. Different isomers can have different smells and tastes, which can be used in certain which can be used to create unique products. Okay, that is the application of geometrical isomerism in three different fields. And coming to the conclusion, we can conclude the geometrical isomerism as an important concept in organic chemistry that arises due to the restricted rotation around a double bond. It leads to the formation of different isomers with distinct physical and chemical properties. The study of geometrical isomerism has practical applications in various fields such as drug design, material science, and agriculture. Understanding the principles of geometrical isomerism is crucial for predicting the behavior of molecule and designing new compounds with desired properties. So that's all about the geometrical isomerism. Thank you so much.